So hydrogen bonding is the electrostatic interaction between two atoms due to polarity. So essentially what happens is that when we have two polar molecules, for example, we have this water molecule, we have this water molecule, and we have this water molecule. And we know that water is a polar molecule because the electronegativity difference between oxygen and hydrogen is greater than 0.4. So since we know that it is a polar molecule, we know that each of the two atoms must have partial charges. So the oxygen, since it's more electronegative, will have a partial negative charge, and the two hydrogens will have a partial positive charge. Same with this one, it's partial negative, partial positive, and so forth. So when hydrogen bonding is an interaction between two molecules due to polarity. So essentially it is a dipole interaction because we have the dipole of one atom interacting with the dipole of another atom. So what we see is that this oxygen, since it has that partial negative charge, it will attract the partial positive hydrogen. And the reason why it's attracting two hydrogens is because we have to remember that oxygen has two lone pairs. Okay, so it has two lone pairs and it's attracting these hydrogens. Same with over here, oxygen has a partial negative, this hydrogen has a partial positive, so it's being attracted by this oxygen. So when drawing out these bonds and interactions, it's important to notice that when we're indicating a covalent bond, we have a solid line. But when we're indicating a hydrogen bond, we have a dashed line. And that's very important because in chemistry, when we're indicating any other bond besides a covalent bond, we use a dashed line. But if we're indicating a covalent bond, it's a solid line. And that's very important. So essentially, then for hydrogen bonding, we have a hydrogen donor and a hydrogen acceptor. So in this example over here, this water molecule, this oxygen atom specifically, is the hydrogen acceptor. And these two water molecules, these two oxygens, are the hydrogen donors because in a way they're donating their hydrogen to interact with the oxygen. And so when we talk about water at room temperature, it is interacting just like this. It's interacting with neighboring water molecules. And as a result, we see this cohesive force. So the cohesive property of water is essentially water molecules interacting and sticking to other water molecules. And that's the cohesive ability of water. That's why we can often see really small, tiny bugs. They're able to walk across water. I believe they're called water bugs. So those water bugs are able to walk across a body of water because the cohesive forces of water create this tension on the surface. So really small water bugs are able to walk across, whereas us humans with our very heavy body weight, we are not able to walk over water. Now, in the liquid state, water forms approximately oxygen forms approximately 3.4 bonds. So the maximum amount of bonds that oxygen can have is 4 bonds. We see 1, 2, 3, 4. So in the liquid state, we see approximately 3.4 bonds. In ice, in solid ice, we see 4 bonds. So what that essentially means is that the ice state is more ordered. We have the maximum number of bonds, and liquid it's less ordered. And 3.4 is an average. So some oxygens may have 4 bonds, some may have 3 bonds. This is just the average. So hydrogen bonding, it contributes to the melting point and boiling point of all molecules. It's important to remember that hydrogen bonding is not unique. It's not specific just for water. We can see hydrogen bonding in any type of molecules as long as those molecules are polar. So any polar molecule will exhibit hydrogen bonding. And when we see hydrogen bonding, it affects our melting point and boiling point. But what's interesting is that a single hydrogen bond alone is actually a weak interaction. Our covalent bonds are actually a lot more stronger compared to our hydrogen bonds. But when we have many, many, many hydrogen bonds together, this will increase our boiling point and our melting point because this increases that cohesive force. It increases the stickiness of water. So water is more tightly bound to adjacent waters, and therefore an accumulation of hydrogen bonding is very strong. Because we have to also remember that these hydrogen bonds, they're not really bonds, they're interactions, and these interactions are breaking, they're forming, they're breaking, they're forming, and it's all happening so quickly. It is a lot harder to break these bonds because they're happening so quickly, and disrupting them is a lot more harder. So if we have hydrogen bonding, it's going to increase our melting and boiling point because it's increasing that stickiness to fellow molecules, fellow polar molecules surrounding. So what's important to remember is that hydrogen bonding is always the strongest when it is linear. So when it is linearly attached to its neighboring molecule, it is the strongest. If the hydrogen bond is bent, it will be less strong. And that is essentially hydrogen bonding. It is a dipole-dipole interaction between several molecules. It is not unique to water. We can see hydrogen bonding in any type of polar molecule. As long as it's polar and it has partial negative and partial positive charges, we will see hydrogen bonding. And hydrogen bonding is going to be very important in our biological systems and within biochemistry.